speaker is Jeremie Lefebvre. I hope I haven't mangled that pronunciation too much. Who will be talking about adaptive myelination, promoting synchrony in large-scale brain networks. I should also add, he's from the University of Ottawa. And with that, the floor is yours.
Okay, well, thank you so much. So my name is Jeremie. It's a great pleasure to be here to be able to talk about my recent work on adaptive myelination and its involvement in neural synchrony. So I guess I wanted to start, before getting in the core of things, maybe by mentioning that this is a collaborative work. It involves a team of different trainees and PIs from different disciplines: math, computer science, animal and experimental work. And we're all, fascinated by this idea of white matter plasticity. And so we've been combining these disciplines towards this particular goal. And so today, this is the menu of my small talk. So basically, first of all, I'm going to talk about white matter and activity-dependent myelination, then talk about the development of a large-scale model of white matter plasticity, and then talk about how this model can help us understand a bit more global synchronization, and maybe some things about resilience and brain homeostasis. So maybe I should just do a recap about white matter and brain traffic. So although many of you might be familiar with what white matter is, so white matter is this like wide structure that we see in this coronal view of the human brain right here. And it's a complicated labyrinth of axons, that are occupying roughly 50% of the volume of the human brain. Mostly myelinated axons. So myelin is this lipid-rich fatty substance that gives white matter its name and color. And the conductive properties of white matter are super important, not only to maintain efficient communications between different parts of the brain, of course, but also to give rise to complicated or complex activity patterns such as synchrony and spatial patterns that we see in EEG, for instance. So if we are to look at one particular axon, this is just like an imaginary axon that I just drew here. These axons are supported by a family of glial cells called oligodendrocytes. So the cycle starts with oligodendrocyte precursor cells that will, mature into full-grown oligodendrocytes. And these are the guys who will wrap myelin around axonal membranes, and they will do so through concentric circles like this. And it will form patches or segments of different lengths between what we call nodes of Ranvier, and this is where the ion are allowed to travel between the axonal membrane and extracellular medium. So if you compare the conductive properties of myelinated versus non-myelin axons, so in absence of myelin, the conduction is rather slow. Okay, so action potentials can also even decrease in amplitude sometimes. So we're talking about conduction speeds in mammals of about 0.1 to 3 meters per second. When there is myelin, we reach much higher conduction speeds between 5 and 150 meters per second. And this is a regime where we have saltatory conduction, meaning that the action potential was actually jump between the nodes of Ranvier and without any attenuation. So now that this, we've done with the refresher, this has been like a lot of recent discoveries showing that white matter is actually a very dynamic network. Okay, so it's far from a passive network of cables, actually a plastic structure that is plastic even after development and well into adulthood. And the general take-home message of this busy slide is highlighted in orange, basically saying that myelination is tuned by neural activity. So there's a complicated axon glia feedback loop between activity of neurons, basically the activity that goes through the axon, actually the conductive property of that axon. And this supports a wide variety of interesting phenomena, such as like training and learning induces bidirectional changes in white matter architecture. There's also environmental external factors, such as daylight exposure can also influence myelin microstructure. And also the interplay between the white matter structure, adaptive myelination, and synchrony as well as a central role in condition. So taking all these elements into considerations, these speak of what we say complementary dimensions of brain plasticity. So if we were to draw like an axis of where synaptic plasticity would be, where we have the different mechanisms of synaptic plasticity dealing with the actual gain of an output or gain of a connection between two neurons, we would have a complementary dimension where we would have more axonal and glial plasticity, where adaptive myelinations, ADM, would regulate the timing of those interactions, not necessarily their amplitude. And we know from the study of complex networks that the timing, so we're talking about statistics of delays, conduction velocities, and so on, are super important for the emergence of collective behavior and oscillatory dynamics that we see everywhere in the brain. So it is with this idea in mind that we've been interested in developing a white matter plasticity model that would connect different spatial scales. So our idea was to reconcile the local effect of adaptive myelination with the large-scale dynamics that we observe at the mesoscopic or centimeter scales. Because even though myelin is formed at the level of cells and axons, so it's a very local process, the impact of those conduction delays become very important as we reach the mesoscopic scale, so basically the large-scale system. So basically, we can think of those axons or those cells forming microcircuits and potentially displaying some form of oscillatory behavior. So, this would be a whole talk on its own, so how this is possible. But let's imagine that we form a circuit with some form of resonance. And these together are embedded in this large-scale brain network. And so the idea is that, okay, so maybe we have different connections between those microcircuits, white matter connections with different cymatic weights, different track lengths, so basically distances between those different microcircuits, and also different conduction velocities. And so the idea would be, okay, so maybe there's a distribution of conduction speeds that would reflect the myelination of those axonal connections. And maybe we can let them evolve or change in time, and some of them could potentially increase, some of them perhaps decrease. But the idea is to have a particular distribution or pattern of myelin formation that would give rise to phase lock synchronization between distant brain areas. Okay, so this is what we are exploring with the simplest possible model, which is the pyramidal model of coupled oscillators. But we enable that model with time-varying delays to take into account this adaptive myelination process. I'm going to go into the details in a minute. So we have different phases, theta I, or basically the angle, and the rate of change of this angle is given by one particular frequency plus a coupling term. And this coupling term is dependent on a phase difference, a delayed phase difference, or see the delay over here, between coupled neural oscillators. And we will measure the synchrony in that network using the order parameter or phase locking value. R, basically 1 being highly synchronized and 0 completely incoherent. We've imported or enriched this model with human connectivity data, importing the COCOMAC virtual brain database, so connectivity weights, basically how different networks are connected, or if connected at all, and the lengths, axonal lengths, basically reflecting the Euclidean distance mostly between two different networks, because we need those lengths to be able to evaluate the time delays, right? Length over speed. But then these particular speeds there are the things we would be where we will be implementing this local myelinating mechanisms. Okay, so we know that the conduction speed, the higher it is, the more myelinated the axon will be. So this is the learning rule, a very phenomenological learning rule that we've implemented, okay, of activity-dependent myelination. It's actually phase-dependent myelination. It's a simple rule that states that the conduction velocity will change in order as a function of the phase difference between two coupled oscillators. So there's a lot of information here, but the general idea is that when the phase offset is negative, so there's a phase lag, then the conduction speed will increase so that these networks can keep up with their phase. We've also introduced some metabolic inertia term so that conduction speed is allowed to decrease if there's no myelin or glial contribution. And also, we made that process super slow, right? Because it occurs much slower than actual neural dynamics. So this is what we did. So we built this network of human anatomy, basically, where a couple neural oscillators. We just chose an initial frequency of 10 Hertz. We're going to break that assumption very soon. We randomized all those phases, and we uniformized all the conduction velocities to 3 meters per second, and we let the simulation run. This value, by the way, is chosen, that is, it fits within the range of very low range of myelinating axon speeds. And we let the system run. And then what we see, oh, sorry about that. What we see is that the system is basically asynchronous. So what you see, the mean phase here basically remains very small. And the order parameter is also very small. So the system is not able to establish global synchronization or phase locking, basically. But we let the system run for a very long time. Now, when I say 10 hours here, it's not 10 real hours. It's 10 hours of scaled times, because, of course, we kind of sped up a bit the process. But after a long period of time, there was like a a wide diversity of connection velocities that were established in the network, and that gave rise to a global synchronous state. So the chromato order parameter increased dramatically after this period of time. So network could basically autonomously reach global synchrony. And this is, when you see the conduction velocities, so this can be seen as a proxy for the amount of myelination in different connections, evolving in time and converging, stabilizing as a global phase locking is achieved, and the associated conduction delays also decreasing. So we evaluated also the statistics of the resulting conduction velocities and delays. There's a lot of stuff, way too much to go into 12 minutes. But the general point I want to make here is that when we look at the statistics, we found that variability in conduction velocity could be compensate for the variability in track length to lead to delays that were very similar between every possible pair of networks, which we thought was very interesting. We then decided to break the assumption of basically looking at one particular frequency of alpha, and we broke that assumption looking at a wide variety of frequency bands and also over a large range of synaptic strengths. And what we see here is basically the order parameter. And you see in blue here, there are regions where synchrony is possible, even for a weak or strong connection gain, and the system is not plastic, when there's no adaptive myelination. And what we found is that by enabling the system with adaptive myelination, so I just encourage you to look to the far right here, when plasticity is a bit stronger, epsilon equals 2.2, now the order parameter becomes very large across the wide range of possible synaptic strengths and frequency bands, and actually enabling the system or making possible the system to achieve synchrony despite the fact that synaptic connections are too weak to permit that in the first place. So in this particular context, adaptive myelination allowed the systems to maintain synchrony over a very rich amount of parameter values. And I'm going to finish on that slide because what these results show is actually interesting in terms of brain homeostasis resilience. So we were interested in looking at the dynamics of this network in the context of white matter compromise, where there would be damage or an injury. So we looked at our network, we made the connection strong enough so that would be some strong synchrony in the network, and then we applied the damage. So basically we destroyed a particular time t, where these triangles are. 80% of the connections were destroyed. And in the non-plastic case, that is when there's no adaptive myelination, the network basically loses its ability to synchronize, and we obtain a completely asynchronous state. In the plastic case, however, while the same damage was applied to the system, the network basically was able to go back to a high synchrony state, maybe not as strong as before, and with slightly different spectral properties, but still. So this is an example of homeostasis that is enabled by adjustment of conduction velocities across the different connections. So on that note, I'm just going to thank my lab members, colleagues, and funding. And thank you so much.
Okay, thank you so much. Very interesting. So
I should stop sharing, right?
Oh yeah, I'll do that. Okay. So you found changes in mesoscopic level behavior by synchrony after 10 hours of biological time that you simulated, is that right?
Yeah, well, it's scale time. This would represent more like 10 weeks of time, but this is not possible. Okay. So we scale the times. We ran the system for a very long time, but we made sure that the asymptotic behavior of the system was not altered by this rescaling. Basically, the oscillatory properties of the network are way, way, way faster by multiple orders of magnitude than the plasticity mechanism, just to make it a bit more plausible.
Okay, so it's potentially myelin plasticity could take the place. Could not take the place of synaptic plasticity. It's always going to operate on too slow a time scale.
Yeah, but at the same time, adaptive myelination can occur at the level of like a few hours only. So it's a faster process than what we think. Of course, it's much slower than synaptic processes, but at the same time, it's also more permanent in a way that when myelin accumulates, it stays there for extended periods of time. So it's a different time scale for sure, from a different axis of brain plasticity, but I think that is very important to investigate.
Okay, thank you. We've got a question from Dimitri. Is there some data on what are the densities of nodes of granvia and axons between different pairs of brain areas that could help to estimate the propagation velocity, at least in part?
There is data about the dynamics of how segment lengths are evolving in time as opposed to thickness and how they are distributed. I could potentially, if I'm contacted by the person, I can lead up to the papers. In the particular study, we did not consider that. We used a very agnostic approach where there's a combination of potential myelin configuration that could lead to the same conduction velocity. Different patches lead to the same timing. So we just focused on that right now, but that's true. We could estimate that using these more detailed information for the distributions of nodes of Ranvier, for instance.
Okay, well, perhaps you can hook up in the side chat to swap the info for that.
Thank you so much.
Any other questions? There's a lot of praise in the chat. I'm just scanning for more questions. So Matteo would like to ask, how did you set initial values for conduction velocities in the plastic case and how much they could change?
Yeah, so in the plastic case and the non-plastic case, all the initial values are the same. And they at the beginning, in the plastic case, they change. In the non-plastic case, they don't change. They were initialized at 3 meters per second initially, which is in the middle range of, so it's a bit slow, and it gives rise to delays that are simply too distributed. So they're too variable. And what plasticity enables is the system to reach more clustered or coherent delays. Yeah. So if you were to increase the conduction velocity to infinity, for instance, and make these connections instantaneous, then potentially you could recover high synchrony without need of adaptive myelination because these connection speeds are infinite. But this is not what the brain is doing currently. It's myelinating some connections and not others, or the same connections at the various degrees. So this is more what we were trying to characterize, at least, as a first pass.
And I think we've got time for one more question. So from Abul Fazl, sorry if I'm mispronouncing that, how do you calculate the distances matrix?
So the distance matrix was imported from the virtual brain or Hokomap database. So there are variables of details, but in some simulations we ran, they basically correspond to Euclidean distance of different nodes or identify networks in the brain. So presumably the distance would be longer, of course, because they're not perfectly straight lines. You could have convoluted paths. This is something that I'm more than happy to introduce in the model later on. As a first start, Euclidean distance kind of did the trick.
Yeah, fair enough.
Yeah, thank you.
Okay, well, thanks again. It's great work.
Thank you so much.
And I'll now